Good morning everyone. This is another lecture on elementary particle. We already have discussed in the previous classes about the four fundamental interactions and the exchange particles of the interactions, classification of the elementary particles, and also we have discussed about different quantum number, isospin quantum number, strangeness quantum number, baryon quantum number, lepton quantum number, okay, and also we have discussed how we can calculate the value of isospin quantum number, strangeness quantum number of a elementary particle, okay. But in this class we will discuss about different conservation law in a fundamental interactions, okay. There are two types of conservation laws. Number one is exact conservation laws. Exact conservation laws means the conservation laws which are conserved in all allowed reaction, such as momentum conservation laws. Momentum is conserved in all allowed reaction. That means the momentum before reaction and after reaction will be same. Number two, energy conservation laws. This is also conserved in all allowed reaction. Number C, charge conservation. Charge is conserved in all allowed reaction. Number D, baryon number. Baryon number is also conserved in all allowed reaction. Actually, baryon quantum number, a number by which we characterize the baryon particle. Number E is lepton quantum number. So these are the exact conservation laws, and these conservation laws are obeyed in all allowed reactions. Now, second type of conservation laws is inexact conservation laws. There are certain conservation laws, those are not conserved in all reactions, such as number A, isospin quantum number, okay. The isospin quantum number is a quantum number that characterizes the isotopic particle such as proton and neutron. Actually, proton and neutron physical entity is one, but the particle manifests in two ways. Sometimes behave as a proton and sometimes behave as a neutron in the electromagnetic field. Actually, physical entity is same, but the particle sometimes behave as a protonic nature and sometimes behave as a neutronic nature. So they are called isotopic particle, and these particles are characterized by quantum number, and this quantum number is called isotopic quantum number, and sometimes it is called isospin quantum number, okay. And isospin quantum number is conserved in only strong interaction. Only strong interaction, the isospin quantum number is conserved. There are four fundamental interactions: strong interaction, electromagnetic interaction, weak interaction, and gravitational interaction. But isospin quantum number is conserved only in strong interaction, okay. I3, isospin quantum number is denoted by I, and this is vector quantity, and I3, this is the third component of isospin, and this quantum number is conserved in strong and electromagnetic interaction. I3 is conserved in strong interaction and electromagnetic interaction. Number C, strangeness quantum number. The strangeness quantum number is denoted by S, and this quantum number is conserved again in strong interaction and in electromagnetic interaction. Purity. Purity is another quantum number, and this quantum number is denoted by pi, and this quantum number is conserved again in strong interaction and electromagnetic interaction. And another one is hypercharge. Hypercharge means baryon number plus strangeness number. Sum of baryon number and strangeness number is called hypercharge, and this is denoted by Y. This quantum number is conserved again in strong interaction and electromagnetic interaction. Okay, thus in strong interaction, the conservation laws, those are conserved. So the conservation laws in strong interaction are isospin quantum number. Isospin quantum number is conserved. Third component of isospin is also conserved in the strong interaction. Strangeness quantum number. Strangeness quantum number is also conserved in the strong interaction. Okay. Purity is conserved. It is actually reflection symmetry operator. Purity is conserved in strong interaction, and hypercharge also is conserved in strong interaction. So these are the conservation laws. Those are obeyed in strong interaction. Okay. Now the conservation laws, those are obeyed in electromagnetic interaction. Only isospin is conserved in strong interaction. Okay. So except I, all the other conservation laws are conserved in electromagnetic interaction. So the conservation laws in electromagnetic interactions are I3, strangeness quantum number, purity quantum number, and hypercharge. Okay. So this is the conservation laws in electromagnetic interaction. Now third one is weak interaction. In weak interaction, only the exact conservation laws are conserved. These conservation laws are conserved in all reaction, all allowed reaction. These conservation may be conserved in strong interaction, in electromagnetic interaction, and also in weak interaction. So the only conservation laws are conserved in weak interaction is these. These are the conservation laws. Those are conserved in weak interaction. Okay. Let me show few example of reaction. Suppose one reaction, pi minus plus proton, and after reaction the particles are sigma plus k minus. I will discuss about the reaction and also the type of reaction. So let's start. For allowed reaction, we have to study basically three quantum numbers must. Number one is charge quantum numbers. Since these are the elementary particles. So charge of the elementary particle always one electronic charge, and negative, then in the unit of electronic charge this is minus 1, plus means plus 1, but the magnitude always the value of electronic charge. So for pi minus, in the unit of electronic charge the minus 1, because these are the elementary particles. For proton plus 1, sigma plus 1, and this is pi meson, so minus 1. Therefore before interaction the total charge is 0, and after interaction total charge is also 0. So the charge change in charge is 0. So the charge is conserved. Okay. Now I will test the baryon quantum number. This is not a baryonic particle. So we know the baryon quantum number is 1 for all the baryonic particles, and already we have discussed in previous class. So this is not a baryonic particle, so the quantum number is 0. Proton is a baryonic particle, so since this is a baryonic particle, so the quantum number is 1. This is baryonic particle, so quantum number is also plus 1, and this is not baryonic particle, so the baryon quantum number is 0. So the B is equal to 0. Okay. Now quantum number, baryon number, and since there is no any lepton particle, so we do not have to check the lepton quantum numbers. Now I will check the strangeness quantum number. Pi meson is not a strange particle. Strange quantum number is 0. Proton is not a strange particle, 0. This is a strange particle, and we know sigma plus have strangeness minus 1, and K minus, actually this is the antiparticle of K plus. K meson have two particles, K plus and K0. These are the particles, and this is the antiparticle of K plus. And since the strangeness quantum number is charge dependent, so the strangeness quantum number is 1. Change the sign, particle and antiparticle. The strangeness quantum number for K meson is plus 1, but this is the antiparticle, so change the sign and strangeness quantum number will be minus 1. Okay, so the change in delta S equal to minus 2. Okay, that means the strangeness quantum number is not conserved in the reaction. But keep in mind one very important thing: for any allowed reaction, strangeness quantum number must be within 0 or plus minus 1. For any allowed reaction, delta S must be 0 plus minus 1. Please keep in mind. So here the strangeness quantum number is, change in strangeness quantum number is 2. So this is not allowed reaction. So this is forbidden reaction. Okay. So this is not allowed reaction. Now let me show another example. K minus plus P omega minus K k plus k0. Okay. First I will check charge quantum number. Charge is -1. Proton have charge +1, -1, +1, 0. Therefore, delta Q before interaction charge is total charge is 0. After interaction charge is 0. So the charge is conserved. Now I will check baryon quantum number. This is not a baryonic particle. So 0, proton is a baryonic particle. 1, this is also baryonic particle. They are not baryonic particle. So the delta B also 0. Baryon quantum number is also conserved. Okay. Strangeness quantum number. K minus. This is the antiparticle of K plus. Actually K plus and K0 are the K meson particle, and they have strangeness quantum number +1. So this is the antiparticle of K plus, -1. This is not a strange particle. The strangeness quantum number of omega minus is -3, and we already calculate the value of strangeness quantum number for omega minus in the previous lecture. Okay, this is K plus, so +1, K0 +1. Okay, so before interaction the strangeness quantum number is -1, and after reaction also the strangeness quantum number is -1. So the delta is equal to 0. That means the reaction is allowed reaction. Now I will check I. This is the isospin quantum number, and isospin quantum number for K minus. Actually K plus and K0 are the two charge state of same physical entity in the electromagnetic field. So there is multiplicity is 2, and these particles are characterized by a quantum number, and this is the isospin quantum number. And if you consider the isospin quantum number is I, then 2I plus 1 is multiplicity 2. So 2I equal to 2 minus 1, 1, or I is equal to half. So the isospin quantum number here half. Since the multiplicity is 2, when the multiplicity is 2, then always the isospin quantum number will be half. K minus half. Proton, what will be the value of isospin of the proton? And you know proton is the nucleon, and there are two nucleon, proton and neutron, and since there are two charge states, so also the isospin quantum number for proton will be half. This is not a isos particle, so 0, again half and half. So before interaction the isospin quantum number is 1, and again after the interaction is 1. So delta I equal to 0. I3 K minus. R3 is depend on charge. K minus minus half. Proton plus charge state plus half, not isoparticle. K plus half, and this is the minus. K0 is the negative charge state. So the I3 is also conserved in the interaction. Okay, so the reaction proceed via strong interaction. Again, let me show another example. Omega minus this is xi 0 plus pi minus. First I will check the charge. Minus 1, 0, minus 1. So delta Q is equal to 0. Okay. Baryon quantum number. This is the baryonic particle. So the baryon quantum number is 1. This is baryonic particle. So quantum number is 1. And this is not a baryonic particle. So 0. And delta V is equal to 0. Strangeness quantum number. Omega has strangeness quantum number is minus 3. Xi strangeness quantum number is minus 2. And this is not a strange particle. So the delta S equal to 1. Change of the strangeness quantum number is 1. So the strangeness quantum number is not conjugate, but for Allard reaction we know the delta S will be 0 plus minus 1. Okay. So this is the Allard reaction. And so we can say this will be the weak interaction, because we know for strong interaction is the strangeness quantum number is conjugate, and also in the electromagnetic interaction strangeness quantum number is conjugate, but here the strangeness quantum number is not conjugate. But the value of the strangeness quantum number, change in strangeness quantum number after reaction is within the 0 plus minus 1. So the reaction is allowed, and the reaction is go through weak interaction. So this is the example of weak interaction. Now I will show another example. Pi 0 equal to develop 2 gamma photon. First I will check charge. Charge is 0, photon has no charge, so 0 0 charge is conserved. Okay. This is not a baryonic particle, 0. Photon is also not a baryonic particle, so delta B is equal to 0. This is not a strange particle, so 0 0 0 delta S is equal to 0. Okay. But isospin quantum number, this is the pi meson, and we know pi, there are 3 steps: pi plus, pi 0 and pi minus. There are 3 charge states in the electromagnetic field. Actually the inherent particle is 1, but they manifest in 3 different ways in the electromagnetic field. So they are isoparticle, and the particles are characterized by quantum number, and this is the isospin quantum number, and here the multiplicity is 3. Okay. So 2i equal to 2 and I equal to 1. Isospin quantum number for pi is 1. So when the multiplicity is 2, then isotopic quantum number will be 2, but when the multiplicity is 3, then the isospin quantum number will be 1. So the isotopic quantum number for phi 0 is 1, but photon is not isoparticle, so the isospin is 0 0. That means delta I not is equal to 0. This is allowed reaction, because Q is conjugate, charge is conjugate, baryon number is conjugate, strange number is also conjugate, but isospin is not conjugate. So this interaction is go through electromagnetic interaction. Okay, electromagnetic interaction. Please keep in mind 2 things very important. Number 1, if any reaction there is photon. Presence of photons means, actually we know the photon is the exchange particle for electromagnetic interaction. So the absorption and emission of photon develop the electromagnetic force. So in a allowed reaction, the presence of photon indicate the interaction is electromagnetic interaction. So this is the electromagnetic interaction. And second one, in a reaction, in a allowed reaction obviously, the presence of the neutrino particle is the example of weak interaction, because the neutrino particle is developed only in the beta decay, and beta decay is, we experimentally verify this is the weak interaction. So these are the two very important points. For any allowed reaction having photon is electromagnetic interaction, and in any allowed reaction presence of neutrino is the weak interaction. Suppose neutron decay into proton plus to conservation of the charge, because the neutron has no charge, so electron will be developed and neutrino, obviously this will be the antineutrino. In any allowed reaction like charge, baryon, lepton number is also conserved, and electron, muon, tauon and the corresponding neutrinos are the lepton particles, and in each allowed reaction the lepton quantum number